Thanks everyone for coming tonight. My name's Adam. I recently joined Town Jericho, and tonight we have expect a very interesting talk. This is Tim Rademacher. He is the scientific director of the Proctor Maple Research Center over in Underhill, and he's also an assistant professor in plant biology at the University of Vermont. Give it away to Tim.
Thanks, Adam. Thanks for inviting me, and thanks for having me. We're a pretty small run, so I will try to keep this pretty informal. And if you have given how few we are, if you have any questions while we go along, I would much rather address them as we go, so that we don't lose anybody and we get a bit of a conversation going. My name, as Adam said, is Tim Rademacher. I was born in Germany, where there are no maples. Well, that's not true. We do have some maples, but mostly planted Norway maples in urban settings, like in North America as well, that then became invasive in the forest, but certainly no sugar maples and very little maple sugaring. I have only been working on maple sugaring fairly recently, actually. So I did my undergraduate in plant sciences at the University of Cambridge in the UK, and then also did a PhD there, and actually focused on climate change, so the second part of what we're going to talk about. And my PhD was basically looking at interactions between the atmosphere and plants, and how they interact, how they exchange gases, but at a global scale. So I didn't work with plants directly, I worked with computer models. Some of these models that we use to project how climate will behave into the future. That was really fun, but very abstract. So I wanted to get my hands a little bit dirty, and after my PhD I moved to the US, from Cambridge to the other Cambridge in Massachusetts, and started a postdoc there to actually look at the cellular level dynamics of how wood grows. Because one of the big takeaways from my PhD was that we don't really understand wood growth very well, and that's really important when we want to know how much warmer it will be at the end of the century. Quite often in those projections we talk about it could be 2 or 8 degrees warmer. That's a huge range on average, right? So my aim was kind of trying to figure out what are the reasons, why can't we figure it out more precisely, why is there such a huge margin of uncertainty? And one major aspect is clouds. We don't understand clouds very well. Another one is tree growth. We understand it empirically for silviculture. We're good enough to say roughly how much growth there will be, but we don't understand it mechanistically, which means that actually projecting it forwards becomes really difficult because the conditions are going to change. So I focused on that, and on the way got interested in how carbon moves within a tree. You know, from being photosynthesized in the leaves to then being non-structural carbon reserves, and that's where I started getting interested in red maple. And I realized that when we do maple sugaring, we use some of that carbon in the form of sugar. And I then moved to Canada and fell into the evaporator and started studying maple science. Like, maple syrup is pretty sticky, so once you fall in there, it's difficult to get out of it. And I've been studying it ever since. And yeah, started recently at the University of Vermont, so I've been here for 6 months now. So this is all still pretty new. So as a quick preamble, my position started, I've been only here, it's actually not quite true, it's been now 6 months, so a little bit longer, but it's still all pretty recent. So most of what I'm going to talk about today is either known knowledge or stuff that I have done before. There's no new stuff that we have done at Proctor yet, because 6 months is just not enough time to do rigorous science. I hope that there are no mistakes in what I tell you today, but if there are any, they are mine. So come and talk to me. That said, there are loads of people that have contributed to this, and I want to make sure that I thank them before talking to you. Okay. The last little warning is I want to talk about what happens in and to the forest side of things today. Climate change could also have an impact on supply chains, on where we get our plastic tubing from. There are loads of other aspects of it, but they are much harder to study, and I want to start with just the forest around us and how the changes will actually affect that system. So that will be the main focus of the talk. Before I dive into actually talking about that, quick little bit, a tiny bit of history on UVM and maple research. So maple-related research actually started in the late 1800s at UVM, so it's been quite a while. In 1946, the Proctor farm was donated, which is on Harvey Road in Underhill. It's a 200-acre property. And in 1947, the research center was founded, the Proctor Maple Research Center. So it's now been 77, we're going on to 78 years of research at the Proctor Maple Research Center. We had the 75th anniversary in 2023. I started last October. I hope to make it to 2048. Then I can celebrate the 100th anniversary. That would be pretty cool. So, and that would be good. Like, I would be happy to then retire, I think. So that's the aim. If you've never been there before, this is what it looks like from above. This is Pleasant Valley Road. This is Harvey Road going up. And this is basically the property. It is at about 1,500 feet of elevation on the slopes of Mount Mansfield. So the peak of Mount Mansfield is somewhere up here. The main bush is just above the research station and our sugar house. This is what has been tapped for quite a while now. But for the last 20 years, we've actually changed how we tap things quite substantially. First of all, we've acquired some additional land, which we have started tapping as well, which means that we actually increase the amount of taps we have. So it's in total, nowadays we are at 206 acres or something, and we tap about 7,000, just shy of 7,000 trees. Most of them are in this upper part and in these two bits. We started tapping down here as well, but the trees are still growing and they are still pretty small to be tapped. So it's not very intensive. And there are some areas that for topographic reasons it's really difficult to get tubing to, so we haven't tapped there yet. The mission of the PMRC is threefold. We do research, that's kind of our main bread and butter. We do education, so I'm actually developing a first maple class at UVM in 20 years or so, which is quite outrageous that UVM doesn't have a maple class, but we're working on it. And then outreach. These kind of events, talking to sugar makers, that's part of what we do as well. In terms of research, the center in the past 20 years has really contributed a lot to innovation and progress in the industry. So a lot of innovations to improve yields have come out of Proctor. That's an axis of research that I hope to continue, but I'm also very interested from my background in the sustainability of the industry. How can we make sure that it is and stays and will be sustainable? And sustainable, that includes economic, ecological, and social sustainability. So the three pillars of sustainability. By the way, this is our sugar house, and that's what it kind of looked like today, minus the snow. And actually, we've changed the chimney since this, so we don't have that chimney anymore. So today, I thought I will start by talking a little bit about context to situate you in terms of where we are at the moment. Then I will talk about observed changes, things that we've already observed when it comes to maple sugaring. And then we'll talk about anticipated changes. What are we thinking are the next steps that we will probably observe? And then finally, some mitigation and adaptation strategies. What are some of the things that we can do to prepare for that change? So in terms of context, I think one of the key words is rapid evolution of an industry. At least two of you tap with buckets. And that is still the prevailing image that we have when we think of maple sugaring. Quite often we have that image of, a bucket, we have the sound of the dip, dip,
Grandma
dip.
Moses.
Yeah, exactly. No, and that's like that bucolic image is still very much ingrained. However, the industry, if we look at the growth of the industry, let's start with the gray and blue line. The gray line is Canadian production of maple syrup over time. So from the 1920s all the way to the 1980s, it was pretty stable at about 10 million liters. By the way, a liter is kind of a quarter of a gallon-ish. So it was pretty stable for, a long time. And then all of a sudden, it started increasing. The blue line is Quebec. So as you can see, Quebec makes up pretty much all of the Canadian production. There's a small difference between the two lines, but it's not very big. So Quebec is really by far the biggest producer of maple syrup in the world. The US, I don't have as much historic data, but it has followed this quick increase in the last couple of years. And this increase keeps going. Vermont is by far the biggest producing state in the US. And in Vermont, and I will show a graph of just Vermont in a second so that we can see the growth in Vermont. But Vermont produces about 50% of the US production of maple syrup. So half of what's done in the US comes out of Vermont. And most of that comes out of a few counties. So Chittenden, Lamoille, Franklin, basically anything close to the Canadian border, that's where really maple syrup is made in the US. In Vermont, close to the Canadian border. Interestingly, it hasn't grown as much everywhere. If you look at Ontario, for example, and by the way, Ontario has way more maple trees than Quebec. So do New York and Maine. They have way more maple trees than Vermont. But they are not the leading state in the US, neither is Ontario the leading state in Canada. Ontario, as a matter of fact, produces less maple syrup now than they did 100 years ago. And it's marginal, but it is a little bit less. So it's not everywhere. It's just in certain places that we see this quick, rapid growth. But this rapid growth is due to a couple of things. It's really become an industry. One of the main drivers of that is this line here symbolizes the foundation of something called the Producteurs Productrices Acéricoles du Québec, which is a federation of producers in Quebec. They banded together and they have a monopoly. They have a cartel, they control the maple syrup price since 1989. That controlling of the price meant that you could, before, if you had a good year, the market got swamped with maple syrup and the price went down. And if you had a bad year, the price went through the roof. But that meant that actually it was really difficult to invest because there was such a high volatility. So what the Québécois did in '89 is they said, we are going to establish the International Maple Syrup Reserve, which the Strategic International Maple Syrup Reserve still exists till today, and there's millions of liters of maple syrup in it. And in a good year, they put stuff in it, and in a bad year, they take stuff out of it, and that way they control the price. So even in Vermont and in the US, the prices that you get from a bulk seller are basically the prices that the Canadians decide, and when I say Canadians, I really mean the Québécois, decide what the price should be this year. So they have normally a 3-year market agreement, where the federation negotiates with the buyers on what the price should be. And that at least means that you know what you will get for your syrup. So that gives you some investment certainty. There are also a couple of other things that have played into this rapid increase. Technology has changed a lot. 99% of what's produced here and in Vermont as well, but what's produced in terms of commercially produced maple syrup is done with high vacuum tubing and reverse osmosis on highly efficient evaporators. The buckets still work. You know, your kitchen stove works. We can do it over an open fire and we can still have fun with that. But in terms of the industry, that's really hard to make a living of it. I've made a lot of really hard syrup, which was very expensive, if I would have charged my labor time at least, long hours. But if you want to make a living with it, then a lot of the technology has featured into that. Before I move into that and talk a little bit more about it, one last thing is, if we go further back and look at US and Canada data, so the dotted line is US, the dashed line is Canada, then more than 100 years ago, we actually think that the US produced more maple-derived products. Why do you think that is the case?
They had no dairy farms.
You're onto something. Elaborate. Explain.
Farmers used to sugar to pay their taxes, I think.
Yeah, and because they had nothing else to do at that time of the year, and that was a source of sugar, right? Yeah.
We have much more forest.
Actually, we are pretty forested now as well. So it's more about the people tapping the trees. So we actually think that in the US, 100 years ago, way more maple trees were tapped than today. Just that they were tapped by farmers for subsistence, by families that used the sugar themselves. Also, they didn't make syrup necessarily, they made sugar. Because sugar is more stable, more easy to transport, and it's just more easily used as well. So we think that about 100 years ago, just every little family where they had a woodlot, they would tap in it. So the thinking is that actually we probably tapped twice as many trees in the US 100 years ago than we do now. There is still, that's to a degree debatable because it's very difficult to get good data on that. But I also want to acknowledge that basically this has been going on for a very long time, maple sugaring. But the industry has evolved really quickly and is completely different today than it used to be even a generation ago, 25 years ago. It was a very different industry. So we are not necessarily tapping more trees than we did 100 years ago, but we extract the sap in a very different way.
And so, I just wanted to ask,
yeah.
So when you say made sugar, you're thinking that they boiled it until it became like candy, basically, and then broke it up?
Yeah, so if you keep boiling it after syrup and you continue extracting the water, basically, eventually it really becomes sugar. And it was easier to transport because you can make bricks of sugar. And then a brick of sugar you can just wrap into paper. It's much easier to deal with, also to divvy up, than if you have a sticky liquid that you need to deal with. So we know that people did that. The scale of it is still something that is very difficult to really figure out, but we see it so much in historic records that basically anybody who seemed to have a dairy farm or who seemed to have a farm lot, but with some woods, seemed to also tap the woods. Yeah. So if we look at so this is just blown up for the last couple of years for Vermont and New York. New York and Maine are number 2 and 3 in the US. Vermont is number 1. But we can see that it didn't start quite in '89 for Vermont. It took a little bit of time. But eventually the Americans realized, wait, the Quebecois are establishing a market, the stables are, the prices are stable, and people started expanding here as well. So this is the total production of maple syrup in Vermont, which has increased massively. So over the last 20 years, we are producing roughly 6 times as much maple syrup than we used to 20 years ago. So there's a really quick expansion, and that's mostly in this kind of northern area of Vermont. And that's still continuing. How much it will continue into the near future is everybody's guess. Tariffs are very, very difficult for this industry to predict what they will do, because on the one hand side, the Canadians control the price and the equipment. The only American company was bought by a Canadian company not long ago, so there is no American company producing equipment. And if you want to expand, you need to buy equipment. And that equipment is now quite a bit more expensive. At the same time, the syrup coming down the border is also, hit with a tariff. So how that will play out. But expanding at the moment was not limited by, by necessarily the market. The US market is still unsaturated. So the Quebecois, they bring about 60% of the syrup sold in the US comes from Quebec. But it's growing every year. And even if we wanted to, it would take decades before we had the production here to satisfy that demand. And that demand is unsaturated. Every year, the more syrup we produced, we were able to sell it. We haven't hit a roof yet, where at some point there was so much Canadian maple syrup that we couldn't sell it anymore. So there seems to be an appetite for it. And there is still a huge opportunity for growth as well. If you break that down, how did that production increase? Two factors are, first of all, our yields have increased. So what I show here is the yield in gallons per tap. And you can see that both lines have a very slight tendency to go up. So it's not massive, but we started at somewhere between 1.5, 0.15, 0.2 gallons per tap, and we are now more in the 0.4 range. So we more than doubled the amount of syrup we can make from a single tap hole. And that's due mainly to high vacuum tubing. High vacuum tubing allows us, on average, like in our studies at Proctor, we've shown that we get twice as much syrup from the same tree with a high vacuum tap than with a bucket, or with a gravity tap, as we would call it. So that's one big change. Another big change is the number of trees that we are tapping. So that has increased from somewhere around 2 million trees in Vermont in the around 2000 to now we are up to somewhere around 8 million trees. And that's probably an underestimate still, because I didn't count the 7 you have in your backyard. Neither did I count. Yeah. So there are a lot of smaller operations, that don't go into these statistics. And so there are clearly still more trees that we are tapping. The potential is also still way bigger. But, we have more than, we tap more than 4 times, or about 4 times as many trees now than we did 25 years ago. So that's kind of an industry picture at large. It's a long and rich history. It started with indigenous peoples that showed Europeans that there's this sugary liquid. They adopted, is probably the word I should use, adopted it and made a tradition out of it, changed it. They brought modern equipment to it in the last 20, 25 years, and in the last 20 years it has really become an industry. Before then, it was mostly subsistence farming. It was something that you did with your family. It was something that you did as a cultural activity, but it has become an industry that supplies big supermarket chains like Walmart and Costco and so on.
What was the technology the Abenaki used?
It is, given that there are no written records, we have some knowledge of what Europeans found when they came here. There is quite often talk of basically using axes to cut a V-shaped injury into the tree, and then it put a little piece of wood into that, so that the sap that would run out of it would then be directed by the wood away from the stem and not just run down the stem. And they quite often used wooden baskets made out of birch bark. However, most likely they didn't produce syrup. Because boiling, and I will come back to this at the end of the presentation, but boiling sap to syrup is a very, very energy expensive process. It takes a lot of energy, and before metal kettles and so on, that would have been incredibly difficult. We think they reduced it to something that we would nowadays call concentrate. So most likely by heating stones in the fire and having hollowed out trees with the sap in it, and then putting the warm stones in to evaporate the water, to heat it and evaporate it. But that would have been a very, very arduous exercise. So most likely they didn't get anywhere near the concentrations of sugar that we see nowadays. At the same time, this is the greenhouse gas emissions for Vermont. And I only wanted to put this up here to basically have a quick kind of contextualization. We live in an area where most of the greenhouse gas emissions actually come from residential, commercial, and transportation. Those are the 2 big sectors. But agriculture, which is the green here, so blue is residential, commercial, and industrial, and the purple is transportation. So those are our 2 main sources of emissions in Vermont. with agriculture being third in green here. And maple sugaring is part of that agriculture. And these greenhouse gas emissions have meant that globally we've seen temperatures increase. So globally, this is what temperatures look like from the 1850s till, this is up to 2023. I didn't have data for 2024 yet when I made this graph. But this, basically the zero line here is the 61 till 2010 50-year average. So before that 61 till 2010 year period, we were constantly below that average. And since we are well above it. That's globally. If we just look at just Vermont, so this is temperature data for Vermont, there also seems to be an increasing trend. So this is kind of the long-term average. The vertical line here is the 100-year average for Vermont from 1901 till 2000. And the orange dots is every single year. So while we have a lot of going up and down, we have like different years, some are warm, some are colder, there is a clear tendency that we are getting warmer and warmer, especially in the last 20, 30 years or so. At the same time that it's getting warmer here, gradually, it's also getting wetter. So this is precipitation. Again, the vertical line is the long-term average kind of for an entire century. And that's at about 41, 42 inches of rain a year. But in more recent years, we get some years like where we go almost up to 60 inches. But again, there's a lot of variability. There is kind of a long-term trend, but there's a lot of variability. So we also get some really dry years. But there is a slight tendency for more rain. So all of that, one of the big consequences of that is that it affects biodiversity. It affects the ecosystems around us. So one of the things that globally we can observe is that insect and bird populations are declining. And when we look at bird populations, it's particularly those that eat insects that tend to be declining, which is probably related to the fact that insects populations are declining. There are a lot of potential theories on why that is. It's also something that's really difficult to show with data because there were not that many people that for their entire life consistently collected insects in the very same way to show how the abundance has changed. But the more we look at this question, the more it becomes obvious that there seems to be a decline. And we're hypothesizing that at the moment, because extinction rates of animals, of organisms in general, are normal. Throughout evolution of the planet, like we've always lost some species. We don't have dinosaurs anymore. Like it's normal that some species go extinct, but we hypothesize that at the moment, we are killing roughly 100 to 1,000 times as many species as would be the normal background rate. So some people say that we are in what is one of those periods of the planet Earth that's called a mass extinction event, where a lot of species are dying. One of the ways of measuring that, and this is a bit of a controversial way, but just to give you an idea, it's called the Living Planet Index. It is developed by WWF, so part of the reason why it's controversial is because it's made by an environmental organization. But they basically calculated in the 1970s for the first time this index, which is based on monitoring almost 32,000 populations of different species, 32,000 populations of more than 5,000 different species. And they monitored all of these species and basically showed that there is a constant decline over time. So that's the general context that we're in. So now what does that mean for maple sugaring? So let's talk a little bit about the changes we have already observed. How has it affected ecosystems around here? What has it done? So the very first thing is when we talk about maple sugaring, we need to think about what gives us maple syrup yield, what I would call sap yield. Depending on how much sap I get, that will determine how much syrup I get out of it. And there are two major factors. One is sap sugar content, how sweet the sap is. If my tree is sweeter, I will get more syrup, even for the same amount of sap. And how much sap I get, the sap volume. Now, those of you that have done, like, that put up their buckets, you all know that the sugaring season is not one continuous flow. Like, there are these discrete events where we will get sap, and some of them are bigger, some of them flow faster, sometimes there's nothing, and the sugar content will also vary throughout the season, so it's not always stable. It's roughly around 2% somewhere, 2% sugar concentration in the sap, but it varies. So that's the general sugaring season. One of the things that we already observing and that we think will continue in the future is that actually the start of the sugaring season, what used to be our traditional start point, we get now earlier and earlier events. And theoretically, you can make maple syrup anytime the tree doesn't have leaves, and you get a freeze-thaw cycle. So you can tap your trees in the fall. I would not recommend doing that. And I will come back to why I wouldn't recommend doing that. But theoretically, you can. But the standard season is spring that most people tap. And the spring season has been shifting forwards. And that's something that we have a lot of anecdotal evidence for. And I'm just writing up a paper based on data from more than 10 states and 5 provinces in Quebec, from more than like tens of thousands of companies looking at their historic records to really show a robust trend that shows like we are tapping earlier and earlier. And we think that it's about, like, compared to 100 years ago, almost a month earlier now, the heart of the season. The heart of the season. So we do see that. If we break it down, because we think about maple sugaring mostly at the end of winter and the beginning of spring, but the trees, they experience the climate all year round, right? And there are things all year round that the trees will experience that will actually affect them. So if we start with winter, in winter we tend to get less snow and more precipitation. In the last couple of years there were some really spectacular events of winter rainfall that caused inundations around this area, right? Or in Vermont, I should say, rather. But that's something that we see more and more, so less snowpack, more precipitation. One other thing that comes with that is basically have less snow cover in general. Snow cover is quite important for maple sugaring, or can have an influence, I should say. In spring, we get earlier snowmelt, we get an earlier start of biological activity. So we do see, and it's very temperature related, but the leaf out, when the leaves come out, that has also been moving forward. And I don't know whether you've ever, are you ever pulling the season so far out that the leaves are starting, the buds are starting to burst? No. If you do, the taste of the syrup changes. And it's called body syrup, and it's not very nice. But that period is actually moving forward as well. So not only the start of the season is moving forward, also this biological activity is moving forward, which means that actually the season doesn't seem to be changing in length much, but it's certainly advancing. And we get late frosts, which can be problematic, more late frosts. In the summer, we have more and longer heat waves, more summer droughts, and more intense rainfalls. The summer droughts can directly affect the tree. The rain can make it more vulnerable to, for example, wind throw. If the ground's really soggy and then a storm comes through, the tree's more likely to blow over. And then in autumn, we do tend to see a later start to the cold season, also more drought. Quite often the autumn is actually the driest part of the year, and more hurricanes or high wind events. So what that did to the sugaring season, and I already said this, but basically on average it starts a bit sooner, but the length is pretty stable. Problem is talking about length with maple sugaring is really tricky because it's all of these discrete events, right? And sometimes you don't have a week and then you have a week again. So talking about the length is in some ways quite misleading, I find. But the time difference between the last and the first date, they haven't changed much. They have just moved forward. And there's still a lot of uncertainty, and I'll come back to this when we talk about how this might evolve moving forward. But before we do that, I wanted to pass these around. Anybody knows what this is?
Looks like a piece of wood.
You're right.
Stain from tapping.
Yeah, so this is an old tap hole. And this is what the wound on the inside of the tree looks like. The important thing with this is when you tap, you need to make sure that this injury is on average in the long run smaller than the new growth of wood, because otherwise it becomes unsustainable because you're taking away more on average than the tree reproduces. So two major factors for the sustainability of maple sugaring are how big are these zones of compartmentalized or stained wood, and how fast is your growth rate. This one we have a handle on, we can actually influence, because the smaller we make our tap hole, the smaller this zone becomes. And it's a non-linear correlation. So if I go from 5/16 to a 1/4 inch, the volume of the wood that's compartmentalized is reduced by a factor of 10. So just reducing the width, and you can see these injuries go with the wood fiber. So this is kind of the horizontal, no, not horizontal. This is tangential, kind of going up the tree. So you can see that the injury is mostly going up and down, and not actually very wide across. This is also why when we say tapping, like don't tap right above or right below an old tap hole, because you will just drill into non-conductive wood and you won't even get anything out of it. Go a foot up and 2 inches to the left, then you're more likely to, at least if there's not another injury there, right? So that's what that looks like. I will pass that around for those that want to have a look at it. At the same time, if we cut a cookie just out of the stem, you can also see these old tap holes. And you can see that sometimes they can fuse together and create really large zones of compartmentalized wood. That's another reason why we want to space them out, to make sure that they don't fuse on the inside of the tree, because then they can create much larger injuries. You can see one tap hole on this side that's actually, you can also see that the tap hole will never fill in, but it will just grow shut in the like in the front of it. So you can see that on this piece as well. With this tree, you can also see that this tree grew enormously, has really big growth rings, but then in the last couple of years, it almost grew not at all. So growth is also a really tricky thing, but to do a good prediction of what's sustainable, tapping, having a good idea of what the growth of the tree is would be ideal. Unfortunately, we don't really know the growth of the wood unless we take samples. But even analyzing those is not straightforward. So that kind of stuff is really important for the sustainability of it all. And that's one of the tendencies where now modern operations, so traditionally we used 7/16, 5/16. Now a lot of modern operations go down to a quarter of an inch tap holes, or even 3/16. So we have a tendency to go smaller and smaller tap holes just to limit the injury, to make sure that we limit, we increase our chances to be sustainable in the long run. Because the problem is, if you're over tapping, you don't realize that after a year. You don't realize that after 10 years. You might only realize it when your kids inherit the operation and yields start going down. So it's something that is quite difficult to anticipate, actually.
Question.
Yes?
Does a smaller tap produce as much sap as a bigger tap?
No. You are losing out on a little bit of, it depends on from what to what. Like for example, there's about a 10% less sap from a quarter to a 5/16. So you're missing out on 10%, which as a company, that can be huge, right, for your bottom line. However, that doesn't include that you might be able to generate a much better vacuum with 1/4 inch. So a lot of the big companies that's switching to 1/4 inch, they tell me they do that for vacuum, because basically, the better your vacuum level, the more sap you get out. And they say that they actually get better sap vacuum with the smaller taps because they tend to leak less, they tend to be easier to manage. It's less time of their personnel in the forest looking for leaks, so they are convinced that it's economically worth it. But that said, if you just have a gravity tap, a bucket, and you just like a whole bucket like that would give you more sap. It would.
So what's the standard today?
The standard in the industry is 5/16, basically. Yeah, 5/16. That's kind of the standard. And some people have moved down, as I said, to quarter or 3/16. Nobody uses bigger than 5/16 really anymore. But I would say more than 90, if not 95% of the taps in Vermont must be on 5/16. Yeah.
What kind of vacuums are they pulling?
Close to -27, -28 inches of mercury. So -30 is kind of almost an absolute vacuum. You can't really go lower than that. So in an ideal world, we get almost to -29, but it's really difficult to get it that tight. There are always some micro leaks somewhere. So in reality, like down at Proctor today, we were at -27.5. So you are pulling a pretty high vacuum. A lot of people sometimes ask me, does the vacuum level change the injury or the stress to the tree? No, it doesn't. So the single most important thing in terms of the injury is how you drill that hole and how big that hole is. So if you want to help the health of the tree, train your people well in how to do that properly. That is way more important than the vacuum you put onto it. The tree, the internal mechanism of the tree, the infrastructure, is made for enormous pressure because during a summer drought, the leaves suck enormously to get water from the roots all the way to the leaves. Like all that wood infrastructure is made for really enormous pressures. So it's actually used to that to a certain degree. Yeah. So let's talk about some changes to come and consequences. So there are some, I like to divide it into direct effects and indirect effects. So we have direct effects such as maple species will not be in the same places in the future because they are dependent on climate. So in some places, I was in Kentucky in October. They do have a healthy maple sugaring community. The Kentucky Maple Sugar Makers Association has about 1,000 members. A lot of Kentucky farms border onto the Appalachians, and you know they have a woodlot in the back, and they do some maple sugaring. It's not the same industry scale as here. In Kentucky, for example, the standard size is 3/15 because they use different technology, and the standard operation is much smaller than in Vermont, but they do exist. They will be affected very differently in terms of climate change than Vermont will be. So migration of species is one. Changes in the freeze-thaw cycle. We are so dependent on that weather and on these minute temperature variations that how they change will hugely affect the industry. And then there are indirect effects. Things like if we get an insect epidemic, that could massively affect the industry, especially if it's a deadly insect. Let's say it's a longhorn, Asian longhorn beetle that is a wood borer that kills maple trees. You might go out of business for 2 generations because you have to get new maple trees. So those are not like directly affecting it, but indirectly they could be catastrophic. And there are changes to the sugar reserves. So the things that we tap into, those are energy reserves the tree needs for certain things, and they might be affected. So let's start about these things one by one, starting with the species distribution. So if we think about a maple tree sends like seeds in all directions, and then, you know, new maple trees grow in some locations. In science, we call this our climatic niche, like an envelope of climatic conditions where these trees can grow. If ever a maple sends some seeds outside of these climatic conditions, the tree might not germinate, or it might germinate, but the conditions might be too harsh, so it will not survive. So we have this idea of there's, you know, a certain range of environmental conditions within which maple can survive. And they are pretty vast. Maple, especially red maple, is very plastic. Red maple exists from, you know, I don't want to say northern Canada because it's pretty south in Canada, but, you know, Chicoutimi somewhere, the northern range of where humans live in Canada. Chicoutimi all the way to Florida, and I've seen a red maple in Mexico on a mountain. So, like in mountainous habitats, they can be quite adaptive, but there's still limits to where they can survive. So some conditions are too extreme for them. In the future, we think that this climatic niche is going to change, because basically there are some areas where maples are now, which were in the past climatically suitable for maples, but in the future they are not. And there are some areas that might become climatically suitable for maple, but there are no maple trees yet. If I would have to place that geographically, Vermont is most likely somewhere in the middle here, where it will also still be suitable for maple in the near future. But that's also a question of, are we talking 20 years or are we talking 200 years? And to know what happens in 200 years, I would need to know what human decision-making is like in the next 20 to 100 years. So, there is no certainty with this, but you can think about it like most likely we're somewhere in here, and most likely for at least 3 generations there will be maple trees around here that we can tap into. So I don't think that's a major threat in the short term. Maples are pretty resilient. However, if we then look at the freeze-thaw cycles, so let's assume there will still be maple trees around. That's a first, at least, we need them, otherwise maple sugaring is tricky. Then the second thing is, how will the season change? And we already talked about the fact that it starts earlier and it ends earlier. And there was a study done by some colleagues in Canada where basically the blue curve here is the current season on average. This is the start date. And the red and the green are simulations on what that would like in the future. And you can see that the red and the green are actually earlier. So the season is likely to start even earlier. So the trend that we're seeing is likely to continue, and we're going to have earlier start dates. The same is likely going to happen with the end date. The end date is also likely going to be earlier. The length of the season, as we are observing already, doesn't seem to change much to start with. This is for kind of southern Canada, northern US. This is not true for Kentucky. Because the problem is, at some point you can't go further that way. At some point you run out of a winter. And in Kentucky, they are often sometimes tapping in November. And you can't tap the tree in October when there's still leaves on the tree. So again, this is hugely dependent on where you are. But most likely what we will see here is that people will more start tapping around Christmas time. And then, the season might become earlier and earlier. There was one study coming out of Harvard Forest that looked at how that will affect yields. So they modeled kind of the ideal climatic conditions and where the best yields are in the last 50 years. And Vermont is pretty much bang on in the heartland of, where the best production happens. And then they looked at climatic conditions at the end of the century, and Vermont is still in a good area, but the best conditions will be somewhere in Canada where at the moment there are not even maple trees yet. And the problem is we are unlikely, even if we want to plant maple trees up there, and I worked in Canada, and I worked with these people, and they want to plant maple trees up there, they wouldn't survive. Because I talked about this kind of idea of there needs to be an environmental conditions as a whole. Maple trees really don't like waterlogged soils and acid soils. And this up here at the moment is boreal forest with waterlogged acid soils. So you would have to change the soils first, which that takes a while. That's not happening at the snip of a finger. So they are unlikely to go into huge maple production up there quickly, just because even planting trees, they wouldn't survive. However, there are a lot of people that think that this study actually was somewhat exaggerated, because it was basically built let's just focus on this curve here for a second. They basically looked at multiple different sites. These are different sites for which they had data. So this pink site, they had 4 years of data for it. And they looked at how much sap they got and the mean temperature over the season. And they said there is kind of a hum-shaped relationship. However, if you look at the data spots here, and if you just take away the blue sites, that looks more like a much flatter relationship. And this hum shape is really important for their projection. So most likely, There was a second study in Canada using much more data from Canadian producers, and they showed that actually that curve is much flatter, which would mean that actually the production difference that we were seeing in those maps would be much less pronounced. So we would still be much closer to that good spot at the end of the century in Vermont here. But there's still scientific controversy around this. And my best guess is that this is really an exaggeration. And this will be quite a bit further south. How much further south, that's up for debate. It's certainly going to change. But we are most likely at the end of the century still going to make decent amount of maple syrup here.
Are they talking in Canada about genetically modifying trees yet?
No, the problem is even studying that takes such a long time. The problem is you can study genetic modified trees in pots quite easily, but to tap a maple and see whether it's any good for tapping, we have a genetic trial at Proctor. It was planted in 1960. We're now tapping the trees for the first time because it's not a very fertile site. So it takes 65 years to know the results of that trial, which means that, and 65 years in current scientific terms is multiple careers of multiple researchers, multiple funding cycles, and no funding agency in the US at the moment would ever give me money to do a 65-year study. That's just not going to happen. They can be institutionalized, like at Proctor, where somebody does it and hopes that future scientists will reap the benefits of it, but there's no consistent effort for it. There was a lot of study because the sugar content in trees can vary enormously. We generally talk about 2%, but I have one tree that I'm measuring that has above 5% at Proctor, and I have multiple that have below 1%. And that makes a huge difference when you don't have a reverse osmosis, because 5% versus 1%, you need to boil way less, right? And you get way more syrup from that tree. So in the 60s, 70s, there was a lot of interest into finding sweet trees, and then the reverse osmosis was invented, and people were kind of, any liquid is liquid, and I can concentrate it anyways. So it doesn't really matter that much. So we've abandoned that kind of work for a while, but now we're coming back to it. So if we look at those are the direct consequences. If we look at some of the indirect consequences, I'm going to try to keep this a bit quicker because I've been waffling on for a long time, and you probably have better places to be. So there's precipitation. Excessive precipitation is a potential issue, especially when it comes to storm damage. It might facilitate storm damage in the future. There's also this issue of less snow cover because we get more rain and less snow. There was a study that looked at less snow cover by basically they looked at two groups of maple trees and they removed the snow continuously. And I would love to, they did this with small potted trees. I would love to do this in the forest, to pay undergraduates to shovel snow in the forest, just for the fun of it. But basically what they saw is that where they removed the snow, this is the growth of the trees on average. And the group that they didn't remove the snow grew quite a bit more than the group that they removed the snow. And we think that's due to the snow cover protecting the roots. So without the snow cover, frost actually damages the roots, and that's damage that the tree needs to repair. So we think that with reduced snow cover, we might see slightly less growth. And this comes back to growth being important for the sustainability of it all. However, there's still big asterisks here of does this work on potted seedlings translate to forest trees? Because they're two very different things. So as I said, I would love to repeat this, pay some UVM undergraduates to shovel snow at Proctor and see whether it changes the growth rates of trees. One other aspect is late frosts. So this is some damage, as you can see when the leaves come out and then a frost event hits after the leaves came out, and it can kill all of the trees. This then means that the tree actually has to use its reserves to build new leaves. These reserves that we tap into, they are kind of energy and carbon store that the tree uses to build the leaves in the first place. And when this happens, the tree needs to redo that. So that uses up those reserves. And that can potentially reduce the sugar content in the sap that we see afterwards. And there's evidence that this is happening more frequently with the leaves coming out sooner and sooner now, because you still get a cold day every now and then. And then the last one, and this is something that I've been working on in the last couple of years. So we artificially droughted trees. We went into a maple forest in Canada and put up tarps in the forest, like crazy people, and basically intercepted the rainfall from getting to the ground. And then it was channeled away from those trees, and we monitored 13 different sites of either trees that were not droughted or trees that were droughted in this way. And we had soil moisture probes in the soil to measure how much less moisture they got in the soil. And we were able to reduce the amount of rain that hit the ground by 3/4, 75%. So we have, for 4 years now, like there are half of these trees that have gotten, and this is only happening during summer. We take this off in October because this would never withstand snow. Like the snow would just rip through it. So we take it away in October, put it back in May. So from May till October, these trees get way less rainfall. And that's quite realistic because in the future, that's what we expect. If we see droughts, we won't see year-long droughts here. We are not in California. But we might get summer droughts. And I tapped those trees for the first time, not this season, but the season before. And it was quite interesting to see that the droughted trees had less sweet sap. They didn't have significantly less sap. They gave roughly as much sap, but it was less sweet. And it was interesting that it was depending on where the tree was. If it was in the middle of these, the effect tended to be bigger. If it was on the edge, the effect tended to be smaller. I explained that by the roots potentially stretching wide enough that they get outside of the droughted area, so they were less affected. The most affected trees had about 0.4 bricks less, so 0.4%. So that is quite a small effect for something that has been going on for 3 years. We've droughted these trees to an extreme degree in the last 3 years. However, there's kind of a caveat that the last 3 years, the summer rainfall was pretty high. So even just getting a quarter of the summer rainfall was actually pretty close to normal, just because we get so much rain in that particular location. But there seems to be an effect. And those are kind of the more hidden indirect effects. And then the last one is insects, pests, and pathogens. So with what we are seeing with biodiversity loss, that might actually facilitate invasion by other rivals. So one of the things that has been naturalized here is the European spongy moth that has been that was previously referred to as gypsy moth. So that has been here for almost 150 years now and is naturalized, but it can affect the trees. One thing that we haven't seen yet, and if you see any, alert authorities. The Asian longhorn beetle, it has a preference for maple, and it's not emerald ash borer. Yeah, it's different, but it has the same effect. So that's why we don't want it here, because as we've lost pretty much all of the ash in the US, we could lose all of the maple, and that would be disastrous. Luckily, this insect doesn't fly very far, so if you find it, it's pretty easy to contain it. In Canada, it was spotted twice, and they just cut every maple within a couple of miles. And that way it was eradicated on the spot, but that also meant that every maple in a couple of miles got cut. The lantern fly is something that's moving further and further north. So this is something that we originally that is now approaching Vermont slowly, and it's due to warmer winters, it being able to survive further and further north. The lanternfly doesn't kill the tree itself, but can stress it quite a bit by eating the leaves. And then there are unknowns, things that we do not know. One of the things that I wanted to bring to your attention is, if you know somebody, or you've seen this, that you have like small, tiny round holes in your tubing, we would love to learn more about it, because this is something that we've observed recently. We think that it's something called the camphor shot borer doing this, but we want to find actual evidence. So we would like to kind of set out traps. So if you see any of this, or if you know somebody that has seen something like that, get either in touch with me or with Margaret Skinner at UVM, because this is something that is new, and we want to figure out whether this is actually a big issue or just a one-off thing that happened on one particular incident.
Tim, would that hole be within the perimeter of the tree or on the outside of it?
So the beetle itself that we think causes this can actually, and has in this particular case, this photo is like of the spout that's inside of the tree, but we have seen it on the tubing as well. And I mean, we haven't seen it much, so we don't really know yet what's typical. And this is one of the things that we are trying to figure out whether, is this the start of something, or is this just something that has happened once and is really insignificant? Because things in nature happen. Like leaks happen all the time. Like we have coyotes chewing on our lines. Like, that's just part of it. Okay. So last part of the presentation, mitigation and adaptation strategies. So one of the things that we can do is create a more resilient ecosystem. So one of the things we don't want to do is just have maple trees everywhere and nothing else. Because if that happens and the Asian longhorn arrives, that's an all-you-can-eat buffet, and it can just chew through it. So we want to avoid that. So one of the things we can do is by diversifying the landscape. Have some conifers in there, have some red maples in there, have some different maples, have some other species with it. So this is something that especially larger scale operations, we try to tell them. And the problem is at the moment we don't have clear scientific evidence of saying, this is the percentage of trees that helps you to get really resilient. Because obviously every non-maple tree is a little bit less money in the less money in the bank, but it might help for that next infection. The other thing we are still trying to figure out is how does the tubing going to those trees actually affect the wildlife? This is something that we hope to get some funding to study. We know anecdotally that it affects, for example, moose movement, but that's purely anecdotally. So that's something we're still trying to figure out as well. So some of the things that you can do is diversify the structure and composition of the forest. You can do that by, first of all, making sure that you have enough young trees. That's a really important thing, because when big trees die, they need to be replaced. And big trees they die eventually. That's normal. That's part of the process. So you always want to make sure that there are some young trees that can replace the big trees when they die. And ideally, there's a continuous regeneration, so that every time a bigger one goes, there's a small one ready to replace it. The other thing is encourage biodiversity, have some non-maples in there. It's not just good, there are loads of reasons for why that's good. So you can plant and encourage non-maple species or manage the forest for diversity of habitats. Another really important one is leave some dead wood in the forest. Dead wood is really important for insects and all sorts of things. They are then the basis for some predators, which can also be really helpful. Like one of the main nuisances in a lot of tubing sugar bushes is squirrels. If you have a squirrel problem, then often you don't have a predator. If you don't have a predator, that's partially because there's something in your ecosystem that means that that predator doesn't feel at home there. Because if there are lots of squirrels, like normally you would get an owl or a marten or something move in, and I mean they have abundant food. So as long as they find right habitat, they will come. And deadwood is really important for that, for example, because owls do, for example, nest in dead cavity trees and so on. Minimize infrastructure footprint. It is important that you're able to get to your tubing, but maybe reduce the amount of especially permanently access roads, big roads that if you can minimize that, that's ideal. And monitor the presence of pests and pathogens. If you see something you don't know, try to figure out what it is and have a look at what's happening in the woods. Okay, with that in mind, I want to, I have 2 or 3 more slides just to give you an idea of when we look at the maple life cycle and we think about everything from agriculture to transformation to packaging to distribution to the use by the consumer to the end of life, where do you think are most of the emissions?
Distribution.
Transportation, distribution? It's transformation. almost 80% of the emissions come from transformation. And by transformation, I mean transforming sap to syrup. It's boiling. So 80% of the greenhouse gas productions happen during boiling. That's why reverse osmosis is a super means to reduce our greenhouse gas emissions. Now, it usually depends on what did you use to transform it. Is it a little wood-fired evaporator and you cut that wood in your own forest? Then you might actually not add much to the atmosphere because you're recycling what has grown there on site. Or is it fossil fuel? You know, is it a propane stove? Or is it fuel like large oil evaporator?
What is reverse osmosis?
Reverse osmosis is basically a membrane. It's a process that's used to purify water. And in maple sugaring, we use it to do the contrary. It's a membrane with small pores in it. They are small enough that water can pass, but other molecules get stuck. We push sap through that membrane and only pure water comes out, and we have concentrate on one side. And that means that just by pure pressure generation, we can reduce the amount of water in the sap, and we do that to pre-concentrate the sap before we boil it. So a lot of people, like we have a reverse osmosis that we use, and it produces pure water as a byproduct. So for us, we have like a 3,000 gallon tank of pure water that's kind of our waste product, which we just keep around so that we can wash things. But what we are after is that concentrate. And we use that concentrate, so out of the tree we have about 2% sugar concentration. After the reverse osmosis in our operation, we go up to 30-35% sugar concentration. And then we finish it off on the evaporator to 66-68%. But we've already taken out 90% of the water with the reverse osmosis to reduce the time and energy on the evaporator.
Have you measured like emissions based on non-reverse osmosis sap versus reverse osmosis?
Yeah, so there's some work that I'm quoting here by Geoff Lewis at the University of Michigan that looked exactly at that. And the takeaway is basically fuel source of the evaporator, and the higher osmosis you can go, the better. In terms of greenhouse gas emissions. And the fuel source of the evaporator is a huge one. And then again, even if you haven't, there are now electric evaporators, but then the question is, where does your electricity come from? You know, if it's hydroelectricity in Quebec, that's a pretty good thing. And in Vermont, I think a lot of the electricity is actually imported from north. But yeah, and if it's wood-fired, then the question is, where does that wood come from? You know, are you cutting that yourself in your woodlot? Then that's actually a pretty close cycle. Yeah. So there is some things we can do to reduce this. So as an industry at the moment, we actually do produce quite a lot of emissions because unfortunately, this evaporation, most of the industrial scale operations, they do not use wood-fired evaporators where they cut the wood on site. They use, oil-fired evaporators, which actually means that they produce quite a lot more emissions than they reduce, despite the fact that we have this bucolic image of, a beautiful thing. And with our wood-fired evaporator, there is a pretty closed loop. So the industry is maybe not quite as environmentally friendly as we sometimes think. So things that we can all do, and these are things that improve your bottom line, reduce the hours worked, and help you as a kind of for your company. Pre-concentrate the sap with a reverse osmosis, improve the evaporator efficiency. The more efficient your evaporator, the less fuel you use, which also costs you less money. And change maybe the type of evaporator. But those are big investments, especially the last one, that's a big investment because an evaporator is an expensive piece of equipment. So, but by doing some of these things, we can still influence where temperatures will be at the end of the century, right? We still face a choice. And maple sugaring can be part of the solution or part of the problem, in my opinion. We preserve a quasi natural ecosystem, And if we do it right and we process the sap right, then we can be part of the solution moving forward by actually protecting biodiversity, protecting carbon stocks. But we need to make sure that we do that by reducing our emissions as much as possible. However, we can also be part of the problem if we, and I mean, this picture is a bit of an exaggeration. I'm not quite sure what they are burning in there, but yeah. But the point being is, you know, if we don't care about that, then there's also, like, we can actually be part of the problem moving forward. And there's things we can do, you know, engage in dialogue, support the science. Yeah, I will actually leave it at that. I've talked for way too long. Are there any additional questions?
The thing that amazes me about it is the investment.
Oh, yeah.
Because a friend and I would hike in Runamuck's Sugar Woods up here off of Pleasant Valley Road. We ran into some guys tapping. I think it was December they were tapping. And we asked them, because they said they also worked for a company that did the whole work. We asked them how much per tap. And they said, well, why don't you guess? So we guessed $7. And they said, well, if you could get it for that, you're doing really well. So that meant to me $9 a tap for 65,000 taps. And I'm like, whoa. They better sell their syrup somehow.
Yeah, so out of a tap, in Vermont on average, we don't even get half a gallon of syrup. So, you know, you cannot spend that much money on it to be profitable. Like, the industry is growing quickly, so clearly somebody's making money.
Yes.
But it's not a license to print money, by no means. There are a lot of people that are losing money in this industry. It's still hard work, and it's still difficult to make it work. So the problem is it's an integrated chain from, you know, the raw resource of sap all the way to, like, marketing and customer relations at the very end, and business. And there are very few people that are very good at everything, from forest management to, you know, dealing with clients. But most of the good companies find their niche. They find kind of where they slot in that. Some people are better with the forestry side of things, and they just decide to sell their sap and do a sap-only business, you know. And some people are really good at the business side of things, and they actually buy the syrup from other people. So it is very much about finding your niche in that. But it is, to a lot of people, I think maple sugaring is the most expensive hobby they've ever started.
My wife mentioned that last week.
Beekeeping is approaching that.
Yeah, but it is an enormous in terms of an investment. Also, like, if you see as an industry as it's growing, that's big money being invested into this by a lot of different people, right? The biggest sugar bush in the world is in Vermont at the moment. In a single sugar bush, they have they have more than 400,000 taps now.
Where is that?
Northeast Kingdom. Yeah. I couldn't tell you where exactly, but yeah, so 400,000, and their ambition is to do 1 million. So they've been growing quickly.
Are they boiling with steam?
They are boiling with steam, yes. Which a lot of US companies, because it's more energy efficient. So what I was saying about greenhouse emissions, like, the big companies are very aware of this, but also for their bottom line. Because the more energy efficient they can be, the more money they make with every barrel of syrup they produce, right? So they are into emissions reductions not necessarily from an environmental perspective, but just from a business bottom line. In Quebec, there's almost no steam operations because the legal requirements around operating steam are very different, and it's really difficult to get across that legal hurdle of being allowed to do that. So it's a huge investment. So in Quebec, I don't know a single steam operation, but in the US, a lot of the bigger operations are on steam.
So what are they generating the steam on? Just wood-fired boilers, or?
They have boilers, but I don't think they're wood-fired.
Well, yeah. I mean, but like gas-fired boilers and stuff.
Yeah. Yeah, that's what they have steam kettles that are gas-fired, and that's what I've seen in at least 3 different bigger operations on this side of the border. In Quebec now, they use quite a lot of just, the bigger operations use electric evaporators.
Oh, 'cause they got it so cheap up there.
The wood's too valuable as firewood, when you can sell it for $500 a cord or whatever.
Yeah, and this is why, you know, we have this bucolic idea quite often of buckets and firewood, but that's a lot of work. Like collecting those buckets by hand, cutting the firewood before. I mean, it can be a beautiful thing, but it is a lot of work, and especially at scale, it doesn't scale very well. You know, at larger scales, at some points, there are only so many buckets you can carry. There's only so much wood you can split. At some point, you know, when we come to the industrial side of things, it becomes infeasible. Yeah.
The irony of boiling with steam just blows my mind. I mean, what's the process? You're trying to get water out.
Yeah, absolutely.
And now you're using that water
Yeah.
to heat
It
the
is.
status that
Yeah.
you know, you're trying to get.
The reason why it's so popular and why it works quite well is because with steam you can create more closed systems, so you can more easily recuperate the heat loss.
Here's what you have to do. And I have a lot of experience with sub-atmospheric processing, but if you could create a reactor that operates at 50% atmosphere, the water will evaporate 10 times as fast.
This is what the Quebecois with the electric ones do. They depressurize the chambers.
Perfect.
And this is why they get way more energy efficient, but then, you know, they can... The problem is you cannot just... Because some people ask me, you know, why don't we just use a reverse osmosis all the way? Because we don't develop any flavor. The flavor and the color comes from the heat treatment.
Right.
So we need heat treatment. But you can make that more energy efficient by depressurizing the chamber.
Yeah.
And that's something that's been done. But that's also why industrial processing is quite different and more different from your small scale backyard operation, because they are thinking about these scales of efficiency and yeah.
Well, even like 1,000 tap operations too.
Yeah.
Which I know a bunch of guys up in Franklin County, that, you know, 1,500, 2,000, 10,000 taps.
Yeah. People kind of start with the trees in the back and get excited about it, and then, you know, they scale to 1,000, 1,500 trees. Then you hit a bottleneck at about like 5,000 trees, where it becomes very difficult to grow organically, because quite often you need to change for completely different equipment, which becomes a major investment and completely different infrastructure. So a lot of the new companies, they come in with big money, and they start straight away at, you know, like 400,000. They go for the million. They started, I think, 100,000 in their first year, and they are now up to more than 400,000. It has taken a couple of years, but you know, that didn't come organically. That was like big money backing it, like well capitalized.
Would they purchase the land or just lease it?
I don't know whether they purchase or lease. In Quebec, most of the new operations, they own crown lands, and they own public lands, and they don't own the land, but that's much easier to expand. And it's much cheaper than buying the land, because buying the land is way too expensive.
That's
Yeah.
why Trump wants Greenland now, because once it melts, we can all make it.
Yeah, we'll see what Greenland has to say about that.
I don't think they're happy about it.
Yeah. Well, thanks for coming out.